In this work, we introduce Expressive Virtual Avatars, an actor-specific, fully controllable and expressive human avatar framework. Our method takes an arbitrary camera trajectory, skeletal motion for precise control over body pose and hand gestures, and expression parameters, to render high-resolution images of an actor in real time. Existing methods, such as ASH, while capable of rendering realistic human images in real time, fail to provide a fully expressive avatar due to their lack of control over facial expressions. X-Avatar is the first expressive implicit human avatar with part-aware initialization and sampling, but its volumetric rendering slows inference. Another approach mounts 3D Gaussians onto SMPLX with pose-dependent offsets, but fails to capture the dynamic appearance of clothing. Like our method, DeGauss estimates Gaussian parameters from body pose and expressions. However, to address expression tracking challenges, it uses the DPE expression encoder for facial encoding from 2D images, requiring front-facing camera images for accurate driving signals. Our approach defines the human avatar as a two-layer model, an expressive deformable template geometry layer and a novel disentangled 3D Gaussian appearance layer. Given any virtual camera, skeletal motion, and expression parameters, we first drive the mesh template with these inputs, which then serves as an explicit proxy for our appearance model. Unlike traditional unified Gaussian estimation methods, our approach utilizes two specialized independent modules to separately model the body and face, effectively disentangling body and facial appearance. We present results in a novel view synthesis setting, rendering subjects from previously unseen camera perspectives. EVA showcases the ability to produce high-quality renderings of both facial expressions and full-body appearances. Notably, our method captures motion-dependent details, such as the realistic swinging of a skirt, in a physically plausible manner. This approach is ideal for virtual speeches and unlocks immense potential across applications in virtual reality, augmented reality, remote communication, and industries like gaming and film. Even in complex scenarios where the actor partially obstructs their face, our pipeline reliably tracks expressions and faithfully drives the avatar. All the described properties of our approach are equally effective in novel view, novel pose, and novel expression settings. EVA demonstrates the ability to render characters from previously unseen viewpoints, in poses, and with expressions not encountered during training. It faithfully captures the entire human figure while enabling expressions to change independently of body appearance, and vice versa. This addresses a significant limitation of prior methods, which often tied facial appearance predictions to overall body motion. We compare our method against two recent real-time human rendering approaches trained on multi-view data. First, Deep Dynamic Characters, a mesh-based method using embedded graph transformations and vertex displacements for geometry, and dynamic textures for appearance, and second, ASH, a recent Gaussian-based avatar but without explicit control over facial expressions. EVA outperforms both DDC and ASH in novel view rendering tasks. Moreover, EVA excels in novel view, novel pose, and novel expression settings. It captures high-detail facial expressions, where DDC and ASH fall short. ASH infers facial expressions solely from body pose, leading to inaccurate facial appearances, while DDC, lacking 3D Gaussian splatting, fails to capture dynamic details as it relies solely on dynamic textures, compromising realism. Both methods also produce blurry outputs with noticeable artifacts due to the absence of explicit facial expression modeling. Thanks to the disentanglement of our Gaussian appearance layer, we can independently adjust facial expressions and body pose without affecting the other. Specifically, body and facial Gaussians are predicted separately through two independent modules. This enables scenarios such as freezing body motion while dynamically altering facial expressions. Or, keeping facial expressions constant while allowing the motion to continue seamlessly. Furthermore, We have the ability to alter expressions at will, allowing us to create sequences with various facial appearances. We conduct ablation studies to assess the impact of our key design choices. First, reducing the texture embedding size also reduces rendering quality and introduces artifacts. Second, incorporating the IDMRF loss improves sharpness and enhances reconstruction of fine-grained details. Next, omitting expression parameters as driving signals prevents accurate facial appearance reconstruction since appearance is solely predicted from body motion. And finally, a model without disentanglement learns facial appearance from expression parameters and body motion, predicting a slightly inaccurate expression, whereas EVA more precisely reconstructs facial expressions as it's completely disentangled from body motion. One notable example application is actor reenactment, which enables us to drive the performances of multiple actors by transferring both the motion and facial expressions from a reference sequence. In this case, we drive the motion and facial expressions of the two subjects on the right using the performance of the subject on the left as the reference. Thank you for watching.